Very nice. For the very nice introduction. Let me just agree on that. And it's really nice to see all of you after quite some time not being able to have conferences in person. So it's really a pleasure. Let me start motivating a little bit, briefly motivating the topic. And so, actually nowadays, it's really impressive experimentally is the examples of macroscopically delocalized quantum superpositions that can be achieved. One of the remarkable examples is the experiments in the 10-meter atomic fountain in Stanford, where they are able to generate superpositions of atomic wave packets separated by more than half a meter. And then they are able to redirect them, recombine them, and show, coherence, quantum coherence by looking at the interference signal. But even in these impressive examples, in all cases so far, the differences in the dynamics of the different components of the superposition can be entirely described in terms of Newtonian mechanics, quantum mechanics, but Newtonian dynamics. And so, I mean, of course, there are examples of quantum mechanical systems and even quantum mechanical superpositions where relativistic effects can be measured actually very, very precisely, namely atomic clocks. But in that case, the key thing is that the relativistic effects basically act in the same way on the two members, the two components of the superposition, the two different internal states. They are still exposed. Basically, the clock follows the same trajectory at the same position in a gravitational field. So the time dilation effects experienced there are the same for the two members, the two components of the superposition. Instead, the goal that of the experiment that I want to discuss in this talk is actually looking at situations where these relativistic or general relativistic effects act non-trivially on the different members, the different components of a quantum superposition. So, a very good example illustrating this point is actually this proposal to use proper time as switch-way information in interferometry. So I have a diagram here that I will be using all the time, very similar diagrams, these space-time diagrams where you have time along the horizontal axis, some spatial direction along the vertical axis. Typically, it will be the vertical direction, and so the direction of the gravitational field if we're considering experiments on Earth. And then, there are these lines that really denote the central trajectories of the atomic wave packets or matter wave packets in general. And so here I'm not for the moment focusing on any particular realization, how one manages to split and, redirect the trajectories of these central trajectories of these atomic or matter wave packets. But the idea is that in general, in an interferometer, a matter wave interferometer, you would have these different trajectories. They are eventually recombined. And typically the relevant degree of freedom is the center of mass degree of freedom. When, quantized, this gives rise in general to these interference effects that depend on the relative phase, the difference between the phases accumulated along the two paths. Now, the interesting thing is actually when you consider and you exploit the internal structure of these matter particles that let's focus on, or let's consider for the sake of being concrete, atomic systems, atoms. So you can exploit the internal structure to use them as clocks. And then what happens is that actually the description of the experiment then would be, still some quantum state for the center of mass degree of freedom, but then some internal state that now will have a non-trivial dynamics that will encode the dynamics of this clock, this internal clock. And now the interesting experiment is the interesting situation is where the central trajectories along the different arms of the interferometer correspond to different proper times, because in that case, the state of the internal state of the corresponding to the clock will no longer be the same when they are recombined at the two exit ports. And this will have an effect on the interference that you measure. In particular, in general, when the proper times are different, you expect, for example, that the visibility will decrease because the states will not be identical. And so basically you can interpret this as entanglement between the center of mass degree of freedom that follow the wave packets that follow the two different arms of the interferometer and are recombined, and the internal degree of freedom that in a non-trivial state that's acting as a clock. So this entanglement provides, one can interpret that that corresponds to providing which way information, and hence it can lead to a decrease in the visibility of the interference signal. So this is something that the group in Czaslav's group in Vienna a number of years ago, Magdalena, also Igor, who's attending the talk, proposed this interesting idea. So the rest of the talk will be to, first of all, introduce in some more detail the key elements of quantum clock interferometry. Then I will explain what are the major challenges when you really try to implement a quantum clock interferometry experiment to measure effects like the one I described. And then I'll present a doubly differential measurement scheme that overcomes or can overcome all those challenges and is able to measure the gravitational redshift. If I have time, I'll tell you also about the slide variant that has some advantages as far as the practical implementation is concerned in some of the, in certain experimental setups. And then I will finish with a brief conclusion. So let's start first introducing the key elements of quantum clock interferometry. And the idea is the following. In fact, many of the the atomic clocks that are employed nowadays are based on this idea. Consider an atom with two internal states, two different energy levels. That will be the two clock states. They are separated by some energy difference, delta E. And then the idea is the following. You start with your atom in the ground state, and at some given time, at some given point, you initialize the clock. And that's basically done by applying some light pulse, some electromagnetic pulse with a given intensity. And then by adjusting the duration, you can basically drive Rabi oscillations between these two states. And then if you choose the right duration, you can have basically what would correspond to a pi-half pulse, something that creates an equal amplitude superposition, as shown here, of the ground and excited state. In general, depending on the phase of your electromagnetic wave, you will have some relative phase at the initialization, but that will not play an important role in the discussion. Now, the key thing is that if you initialize at some point your clock in this way, and now if you just let it evolve in time, what will happen is that you will accumulate a relative phase difference between the two internal states, basically because they have different energies. And so as after some time tau, because of this difference in energies, delta E, there will be a relative phase that is accumulated between the two. And basically you can use that to encode proper time as this in terms of this relative phase between the two energy states. Notice, by the way, that if, from this state here, it's also very easy to see then that the quantum overlap that was playing a role, for example, before when discussing the visibility, the reduction of visibility is given basically just by the cosine of this product of the energy difference and the difference of proper times between these two states of the clock. Okay, so just to illustrate that a little bit, or just to proceed a little bit further on that, so far, what one has been doing, with actually impressive accuracy is comparing independent clocks. So what I mean is the following, again, these space-time diagrams, but notice that here now purple and orange correspond to two different clocks, two different atoms, for example, that follow different trajectories. So in this example here, it will be one of them is trapped in some way at some constant height, it's held at some constant height, and the other is just freely falling. So it's launched first, and then after some time it falls down, and it meets again, the clock that was trapped. And so you can naturally compare times, when they meet for the first time and the second time, and then compare the proper times measured by the two different clocks. In general, you will have effects due to gravitational time dilation and special relativistic effects due to the different velocities as well. Another example would be this one here, where actually the two independent clocks are held, both of them, all the time at different, at constant height, but different heights. Notice that in this case, compared to the other case, they never meet in the same position. So that means that when you compare the two, it's also important to have a proper way of defining synchronization between the two. And that will actually also play an important role later in the talk. For example, well, basically in an example like this one here, the difference in proper time between the two clocks at two different heights just because of the gravitational redshift, the different gravitational time dilation. If you are in an approximately uniform gravitational field with acceleration g and a height difference Lz, then actually the proper time difference between the two for a total time of order delta t is given by this quantity here. So this is in general a relatively small quantity, but what is impressive is that for optical atomic clocks nowadays that correspond to transitions in the optical frequencies in the optical regime or energy differences of the order of an electron volt, they are able, because they can measure, frequency differences or compare different frequencies with a precision of 1 part in 10 to 18, they are able to measure this tiny effect even for different height differences in height of as small as 1 centimeter. But in any case, even these impressive results, all cases so far here, discussed here, are based on comparing two independent clocks. And instead, what we're interested here is actually considering a quantum superposition of a single atom, a single quantum clock that is, split and then held at different, or basically experiencing different gravitational time dilations, for example, spending time at different heights, and then see the effect when they are recombined on the interference signal. So this is the key difference. Instead of comparing independent clocks, a single clock in a quantum, non-trivial quantum superposition and measuring these gravitational time dilation effects. So far I was focusing, just for simplicity, on the internal states and how the different energies give rise to this way of being sensitive or measuring the proper time. But of course, these clocks are moving. Their center of mass, as we were saying, is a quantum mechanical degree of freedom. And especially if we're interested in these interference experiments, the center of mass is also playing a crucial role. So a more detailed theoretical description involves not only the internal states, but also the center of mass degree of freedom. And so between the laser pulses that can be used for initialization or can also be used to diffract the center of mass degree of freedom, and so split these atomic wave packets and redirect them, recombine. But between these laser pulses, when it's sort of freely evolving, the dynamics is basically governed by a Hamiltonian of this form. So you have a projection on the ground state and the excited state, and then each one of these two Hamiltonians, 1 and 2, the numbers 1 and 2 are we using in the rest of the talk to label the two different internal states. So these Hamiltonians basically are the Hamiltonian operators that encode the dynamics of a relativistic particle with mass mn, where n can be 1 or 2 for the different internal states. And so this is the mass, this is the dynamics of a relativistic particle whose classical action would just be given by this quantity here. This would be, the action if you are in free fall, if there are no external forces acting there. And the important thing is that, because of Einstein's equivalence between energy and mass, this energy difference between the two internal states implies that the mass, the inertial mass of the two internal states, the atoms in the two different internal states, will differ by a small amount, delta m. It will be very small, but it will play a crucial role. Right, so this would be as I said, in free fall if there are no external forces acting there, but actually one can also consider the case where you have some small external forces that are always there because there are always perturbations that you cannot completely screen, or even in cases where you use strong potentials acting as a guiding potential, for example, for your interferometer. So that can be taken into account by including this extra term here. And maybe most of you, I guess, attending this talk are of course familiar with the relativistic expression here, but that of course in the limit of weak gravitational fields and small velocities compared to c would just reduce to the usual non-relativistic classical action with a kinetic term and a potential term for the gravitational field, plus possibly some external potential. And crucially, this term, which is constant, but which gives also some additional contribution, some additional phase accumulation. And it will be important, of course, when you have different or changes in the internal state, because then this mass, as I said, will differ by this small amount delta m proportional to delta A, and that will play a crucial role, as we will see. Right, so let me just briefly actually mention something that it will not be very important for the rest of the talk, but of course, as the underlying solid basis for the results that we'll be discussing is important. And this is a relativistic description of atom interferometry or matter wave interferometry in general in curved space-time, including relativistic effects. The key point is actually that it's very convenient to realize that the evolution of these matter wave packets can be decomposed in a very convenient way in terms of basically two aspects. One is a central trajectory of your wave packet, which basically satisfies the classical equations of motion, including kicks from the laser pulses that act as diffraction gratings. And this is, of course, encoded by some word lines, some trajectory in space-time. And then, in addition to that, this central trajectory of your atomic wave packets or matter wave packets, we will have then the description of the evolution of a center wave packet, following this central trajectory that will basically encode information about how the shape of your wave packet and the expansion of the wave packet is evolving in time. And we will see that actually the crucial thing is that by choosing a frame which is co-moving with this word line corresponding to the central trajectory, there will be actually a very convenient way of describing things. And this will work crucially in the case where these two conditions are met. One is that the velocity spread of your atomic wave packet is much smaller than the speed of light. Notice that that doesn't mean the central velocity. So it can still be an atomic wave packet that is moving, fast, or anyway, those effects are fully taken into account. The only thing that, will involve an expansion that we will truncate is actually in terms of this velocity spread. And just for, comparison, in the typical experiments with atom interferometry, these velocity spreads are typically, smaller than 1 millimeter per second, fractions of millimeter per second compared to the speed of light. And so the corrections I'll be discussing, or the trunk that will be truncated in a moment, will be suppressed by this ratio. And similarly, in terms of comparing the size, the spatial extent of the atomic wave packet compared to the curvature radius of spacetime. So for example, for experiments on Earth, these atomic wave packets have sizes of hundreds of micrometers, 1 millimeter, and the curvature radius of Earth, even on the surface, is of the order of tens of thousands of kilometers. So again, it would be very, very, very small ratio. So usually don't spend much time on these technical aspects, but again, with this audience, the crucial thing, as I said, is actually using for the description of these atomic wave packets that follow the different arms of the interferometer, using a co-moving frame, and technically that corresponds to a Fermi-Walker frame in general, and the corresponding Fermi-Walker coordinates. In that frame, in those coordinates, then the word line that we are considering the central trajectory for each atomic wave packet takes this simple form. It's basically centered at 0, and then the time coordinate in that frame coincides with the proper time along the word line. And they can be used, as I said, for freely falling particles, but even in the case where you have external forces and this word line is no longer a geodesic of space-time and it's accelerated. So in that case, you have this extra term here, and then you have these corrections, due to the space-time curvature. Now, the crucial point, again, elaborating a little bit on what I said a moment ago, is that once you work in this co-moving frame, then the action that describes the dynamics of your wave packet, it's basically you can use a non-relativistic expansion in this way, and in using this, so it's both exploiting these Fermi-Walker coordinates that are well suited, for separations which are not very large compared to the curvature, the inverse square of the space-time curvature radius, the separation from the central word line. And then also when, in addition to that, you consider velocities that are small compared to the speed of light. But again, as I said, this would be just the spread of the wave packet because we are already in the frame where the central velocity is 0. Then you can actually use this expansion, which basically corresponds to an expansion, for small velocities compared to c. And so you would have additional terms involving higher powers of v over c at the cubic, fourth order, and so on. And similarly, in terms of powers of this small separation from the central trajectory over the space-time curvature radius. Yes, Miles, you have a question?
Yeah, sorry, Albert. It's just a basic question. So if you go back one slide, so this approximate approximation where you have a central classical trajectory and then a centered wave packet.
So this is not an approximation per se. I mean, this was anticipating the result, but really what you do is the following, that your wave packet will be following some trajectory. I mean, will just be evolving, and you can decompose this evolution. Maybe that's what you meant. You can, but that becomes clearer in a moment.
But I mean, is it, sorry, is this kind of specially suited to interferometry setups where the particle, the atom is only, it's not interacting. I mean, it's interacting with mirrors and beam splitters, but then in between it's undergoing some free evolution in the gravitational.
No, this is not restricted to that. That's why I was insisting. You can also use it to the case I was mentioning here, and I'll also mention it again, where you have some external force, or even during the evolution between, for example, laser pulses, which can be, can be small perturbations, but actually the whole formalism applies also to the case where these forces are arbitrarily large. You can even use it for guiding potentials, where you really guide, for example, or you can, not just for interferometry, you can use it for the examples of, discussing the two different clocks I was mentioning before, and one of them is trapped at some constant height with some trapping potential. So all that can be described in terms of this general description of evolution of matter wave packets in curved spacetime, including all relativistic effects, even not just for freely falling particles, but even in presence of external forces, which can be large. So it's not restricted to that. In that sense, it's very general. The only approximation basically corresponds to this point, these 2 points here. That's because, as I said, when you, first of all, for each one of the wave packets, you work in this suitable co-moving frame. The technical details would be summarized here for that frame. And then in addition to that, that's connected to this. Basically, the fact that you can use this and you can neglect higher order terms in this expansion for the Fermi-Walker coordinates, it's connected to this point. And you can consider those corrections and see, you can even systematically check that those corrections are indeed very small and how small they are. But basically that justifies then truncating this expansion in that sense. And then in addition to that, you have this additional point, which is that if in the co-moving frame, so the center of velocity now is 0 in that frame, but if the velocity spread is much smaller than the speed of light, which at least for all cases that are relevant to us is certainly the case by many, many, many orders of magnitude, then again, you have also this additional expansion in terms of v squared over c squared. And then again, you could again evaluate the terms that you are neglecting and show that they are very small. And so then you can truncate, and usually truncating at the level which is illustrated here is more than enough. And so that's basically where the approximation is being employed.
Okay, thank you.
You're welcome, thanks. So, right, and so then basically...
Albert, can I quickly ask one question, that these 2/3 and 1/3, where do they come from in the simplifications in Fermi normal coordinates?
So I'm not sure the question, whether you're saying that you wouldn't expect to get those coefficients, or why would you get...
Okay, no. I mean, is there an easy way to understand why those come?
I'm not sure.
Okay.
So right now, I don't think I have a
okay. Don't worry. So maths brings it here. Yeah. Okay. Yeah. Okay. No, go on.
What is nice, but maybe we can discuss that later, is how these Fermi-Walker coordinates are actually constructed based on the Fermi-Walker frame. So that's actually a very nice geometric construction. But maybe, if you are interested, we can discuss that at the end of the presentation. Okay, so now keep in mind then this, this classical action here and these various terms, and then including here, as Maz was asking, so here I kept also this term that would correspond to these external forces that can be large. And, that will give rise to some quadratic part, and even in general can be a non-harmonic potential. So what then that boils down, I mean, from this classical action, basically, just as I said, it would correspond to a non-relativistic particle in a quadratic potential, or in general, an anharmonic potential, plus this constant term. And so the corresponding Hamiltonian then in this co-moving frame has this simple form. You have this C number, this constant term, then you would have in general some additional contribution that would correspond to the external potential, but just evaluated along the central trajectory. And then, so this is again basically a number, a C number. And then that depends on the state, as this one here, the internal state. And then, you know, this Hamiltonian that governs the dynamics of the center wave packet, which is basically given by this quantity here. And again, has the simple form of a non-relativistic particle in general, some quadratic potential, or here I didn't include an harmonic terms, but you can also include them, that's perfectly fine. And notice here that this would correspond if there's some external potential, you know, to basically this Hessian, this secondary partial derivative of the potential, the external potential, but you will always have this contribution here that corresponds to the gravity gradient tensor, which is directly connected to this curvature term here, this space-time curvature term. Right, and so basically with this Hamiltonian here, then you can see that the evolution in this comoving frame takes a simple form, because these two terms will give just this propagation phase here, which is given by this integral, and then you would have then this evolution of the center wave packet in terms of this Hamiltonian. But that's, one can treat that with the standard or the quantum mechanics that one is used to, and then in fact, for many of the aspects that I'll be discussing here, the crucial information comes really from this propagation phase, but it's just calculating this along the central trajectory. Of course, in this suitable comoving frame for each one of the wave packets, it takes a very simple form. In general, however, this proper time or integral along your word line, it will be the proper time that you can calculate in any coordinate system that is convenient for you, for the different also arms of the interferometer and so on. And in general, that will have this contribution that depends on the rest mass energy of the different atoms in the different internal states, and hence it encodes this contribution from delta E. And then in general, if you had some external potential, you will have this additional contribution. So I'm not going to give you more details, but that you would use those tools to basically follow the evolution of the atomic wave packets, the different components of your superposition in general along different paths of an atom interferometer. You can also take into account in this relativistic description the effects of the laser pulses that act as diffraction gratings and generate a beam splitter that creates an equal superposition of atomic wave packets with different momenta that follow then these different trajectories, additional laser pulses that act as mirrors. So these diffraction gratings then that redirect the trajectories of the atomic wave packets, and finally another beam splitter that recombines these atomic wave packets. And then you look at the, you will have a superposition of atomic wave packets at the two exit ports that follow the two arms of the interferometer. The relative phase between the two will be crucial to see the interference signal. And these different phases between the two, you can use the results I presented before, plus contributions from the laser pulses, the diffraction by the laser pulses. And that gives rise to these phases accumulated along the two arms of the interferometer. In general, then, the probability of detecting atoms at one of the, or matter waves, matter particles at each one of the exit ports is given by this quantity here, where delta phi is in general, so it's given by the difference in the phases accumulated along the two arms of the interferometer. And in cases where these two trajectories of the interfering wave packets actually have a non-vanishing relative displacement, you have an additional contribution, which is called the separation phase. It's actually interesting in its own, and even its relativistic interpretation, but for most of the talk here, it will not play a crucial role. So it will basically be the phase shift delta phi that determines this probability of detecting atoms in one exit port or the other will be just given by the difference in the propagation phases along the two arms of the interferometer. So I don't have time to go through this in any more detail, so I want to move to the experimental proposals. But just if you're interested in seeing further details, you can find them here. There you can see, as I said, a fully relativistic description of atom interferometry in curved spacetime, including external forces, even guiding potential, so it's not limited to small forces. And even various aspects, for example, the relativistic interpretation of the separation phase in open interferometers that I mentioned before, but that will not be playing a crucial role in the rest of my talk today. Okay, so then let's move on to quantum clock interferometry now that we introduced the key aspects of quantum clocks. And first of all, explain what are the major challenges if you want to use a quantum clock interferometer to measure these effects, these non-trivial gravitational time dilation effects having an impact on the interference measurement. And so, well, the first one is the insensitivity to the gravitational redshift in a approximately uniform gravitational field, as would be typically the case if you do some experiments here on Earth for atom interferometers that, can have a large spatial separation like half a meter, but not huge. So it's approximately, considering approximately uniform gravitational field is a good approximation. So one can do actually a detailed calculation to and then find that the differences between the proper times along the different trajectories, the different arms of the interferometer in the end is independent of little g, the gravitational acceleration. But actually there's a simple way of understanding intuitively why one gets at the end, after combining all the results, that these contributions from little g essentially cancel out. And the simple way of understanding that intuitively is considering a freely falling frame in that uniform gravitational field. So again, then in this space-time diagram, in this freely falling frame, the trajectories are no longer, the space-time trajectories are no longer curved trajectories, they are just straight lines. And then basically, the proper time along these arms is independent of g. I mean, it will depend, of course, there's some special relativistic time dilation effect in general due to these different velocities of the central trajectories for the atomic wave packets along the two arms of the interferometer. So in some cases, like the example here, that can give rise to a non-vanishing time dilation, but it's independent of little g. Basically, in this frame, when you look at these trajectories, they have no information. You're in the freely falling frame, so the atoms know nothing about the fact that there is actually a gravitational field. There are contributions to the total phase shift that know about the fact that these atoms are in a gravitational field, and that's how you exploit atom interferometers to measure little g, but those are just connected with the phases that the atomic wave packets acquire when diffracted by the laser pulses. So they give a contribution, but they don't have an impact on the proper time along these different trajectories, central trajectories of the atom interferometer. Right, so in this example, you have these laser pulses that act as diffraction gratings. In fact, all of them would act as beam splitters in this case, and so you would have some wave packets that would be lost here, half of them, and those would not play a role, so I will not be showing them anymore. So this would be the example, and this is actually one of the main challenges, this insensitivity to gravitational redshift for typical light pulse atom interferometers. Or if you try to build your quantum clock interferometer using light pulse atom interferometry, which is actually nowadays the typical tool that is used in atom interferometry in precision experiments. So another challenge is actually connected to the differential recoil. And this has to do with the fact that, when you apply these laser pulses, they have some periodic, it basically corresponds to an optical potential with some periodic structure, so an effective wave number, K effective, which is 2 pi divided by the wavelength or half of the wavelength of the laser beams that you use here to build these optical lattices, and that act as the diffraction grating. And so the point is that then these atomic wave you in general generate a superposition of wave packets that, as I said, with different central velocities. The ones that are diffracted will follow a different trajectory because they acquire some recoil velocity that is basically given by this quantity here. But as you see, it depends, of course, on the mass. And the mass for the different internal states will differ slightly due to this delta E divided by C squared. That is, of course, a tiny, tiny effect. It's a tiny quantity, but it turns out that it can give rise to contributions that are comparable to the small effect anyway that we want to measure. So one can see, in fact, that they will follow slightly different trajectories, and these slightly different trajectories then can give rise to a slightly different time dilation effect, even in the case here where you have no gravitational time dilation, purely spatial relativistic. This contribution can be of the same order as the contribution that you would be interested in. And you can see that something similar happens in generically also when you try to measure, if you come up with some scheme where you could measure gravitational time dilation effects as well. So this would be another challenge, or another important point to keep in mind. And finally, the third one, which is more of a practical nature, it has to do with the fact that, well, if you really want to measure this, let's see how small these changes in visibility are for, typical parameters that are, doable in current experiments or in the near future. And so, well, basically, this reduction of visibility, of interference visibility that I was mentioning at the very beginning, is given by this quantum overlap in between the internals, the clock states along the two arms of the interferometer. And so even if you can come up with some scheme that would give rise to some non-vanishing gravitational difference in gravitational time dilation along the two arms of the interferometer, this overlap will be given by this quantity here that I derived before. And once you plug in the numbers for parameters that are, reasonable with atom interferometry experiments that can be, done in the near future, you see that the effect is very small. So if you introduce energy differences that correspond to optical transitions, of this order of hundreds of 400 terahertz or so, and you consider arm separations of the order of 1 centimeter, for example, and you do your, your interferometer, you keep this separation for times of the order of a second, the change in visibility is of this order. So you see that it's really a millionth, less than a millionth. It's really, really tiny. And it's not just that and even if you consider, bolder sort of parameter ranges, like the separations of 1 meter and also total interferometer, or times that you use to keep this different height difference of the order of, again, seconds, you see that even in that case, this change in the visibility is less than 1%, or it's 0.5%. So that's very small. And it's not just that it's, even in this case, it's rather small, but it's also that it's extremely difficult to measure such small changes of visibility with an atom interferometer. And this is because atom interferometers are particularly well suited to measure small phase shifts. So small differences in the phase accumulated along the two arms of the interferometer, but they are not particularly good at measuring or being very sensitive, very accurate to small changes of visibility, because there are many other spurious effects that can actually lead to such small changes of visibility in a practical implementation, and they could easily mask these small effects that I was mentioning here. So from a practical point of view, it's extremely difficult to measure such small changes of visibility. You will need to really push these parameters along beyond regimes that can be easily reached in the near future with the kind of experiments that that have a very sort of have already demonstrated their ability, or in the reasonable future. Okay, so these are the challenges. So these are the difficulties so far. So let's see now actually how one can come up with a measurement scheme, this doubly differential measurement scheme, that can actually overcome all these difficulties and circumvent these difficulties and overcome these challenges. And so this is based on this scheme presented here. So let's go through that in some more detail, and let me highlight different aspects that will play a crucial role to overcome those different challenges that I was mentioning before. And so the first one, before getting to that, let me actually just reconsider again, or rederive, if you want, this changing of visibility in a slightly different way, using basically these tools that I introduced and focusing on the evolution of the different internal states. So the clock state would be still the superposition of different internal states, but now we will follow the evolution of each one of the two internal states. And then, of course, we look at the effect at the end, the interference effect. So then what you can do is actually the probability of detecting your atoms, your clock, at one of the exit ports can be basically written in terms of the probability of detecting the atom in one of the internal states or the other. Okay, so the probability of detecting the quantum clock in one of the exit ports will be, in general, the total probability, the sum of detecting it or having it in one internal state or the other. And so for each one of them, you would have this formula that I mentioned before, the typical formula for an interferometer that depends on the cosine of the phase shift between the accumulated along the two arms of the interferometer for each one of the two internal states, 1 and 2. So then you can actually just use this simple trigonometric expression for the sum of the cosines and rewrite it like that. And then you see that you have this product of two things, one which is basically the mean of this phase shift for the two different internal states, but crucially this factor here that depends on the cosine of the difference between the phase shifts for the two internal states. And in fact, one can see if you substitute the numbers that this is exactly the same quantity that will give rise to this loss of visibility that we saw earlier. However, by writing it in this way, well, it has also some other advantages if you want to look at small corrections and so on. But more importantly, it's actually then one can get the inspiration, as you see here, and realize that that's actually what one can do is that instead of measuring this small change in visibility, is actually do a state selective measurement. And instead of measuring what is the probability of getting or counting the number of atoms at each one of the exit ports, what you do is that you do a state selective measurement, which is a standard thing, and you measure what is the probability or the fraction of atoms that you get at each exit port in one internal state and in the other. And you can measure that simultaneously. So for a given shot, you send a number of atoms or even a single atom, and then you can do a state selective measurement that tells you how many of the atoms or what is the fraction of atoms, the probability that you detected in one exit port, in one of the internal states or the other, okay? And so the interesting thing about that is that on the one hand, it certainly has the same information as the visibility would have. So it contains information about the reduction of visibility, but it has a number of additional advantages. One of them is that from a practical point of view, measuring that is something that you can do much better with atom interferometry for two reasons. One is because, as I said, first of all, atom interferometers are much better at measuring phase shifts rather than changes of visibility. But in addition to that, the fact that you measure each one of these two phase shifts simultaneously, and then you consider the difference between the two, that's something even better. So it's the best thing that you can measure with an atom interferometer, not just a phase shift, but a differential phase shift, especially if you do that simultaneously in a given experimental run, because then there are many contributions, or the main contributions that can give rise to noise and even systematic effects in your interferometric measurement, like for example, vibrations. Those basically affect the two in the same way in this case, and they drop out. So you have this very good common mode rejection that suppresses the main contributions to noise in your measurement of the phase shift, and even some of the main contributions of the systematic effects. So by focusing on performing the state selective measurement and then extracting the phase shift for each one of them and then considering the difference between the two, this differential phase shift is something that is extremely robust and that you can measure very, very precisely. So that's one of the main advantages. And the other is also that by measuring that, it's actually the quantity that you try to measure is also not as small as the change of visibility itself. And that's basically because you're measuring this quantity that would be small. And if you consider the cosine, when this is small, then you just have this expansion, and this would actually contribute to the cosine to lowest non-trivial order quadratically. So you would have the square of an already small quantity if you look at the visibility. Instead, if you try to measure directly this differential phase shift, that will be small, but not quadratically suppressed. So you see, you have all the advantages by performing this state selective measurement and then looking at the differential phase shift. So that's one of the key elements. The other is that instead of initializing the clock before you begin the interferometry sequence, we will actually use these two-photon pulses for clock initialization. Well, here is this diagram for the internal states, but the crucial thing here is really that you have these two clock states, and now these pulses are based on the following: that you use two counter-propagating photons in the lab frame that have exactly the same frequency. And so they basically drive something which is called a two-photon process, a transition between these two. So if you choose the frequency of these two counter-propagating beams to be exactly half of the frequency that corresponds to the energy difference between the two clock states, you can drive transitions between these two. And the important thing about these is that these are Doppler-free effects, so they are not very sensitive to different velocities of your atoms. But more importantly, as I mentioned here, the effective phase that that the atoms acquire when these laser pulses drive this transition, we'll have some non-trivial factors for each one of the two beams here. Then we'll have some time dependence. This will be then the frequency of each one of these photons. But the key thing is that the spatial dependence of the effective phase associated with this two-photon process that is driving the transition cancels out, because basically due to the fact that they are counter-propagating, you have this minus sign here, and if they have exactly the same frequency, the same wavelength, then this spatially dependent part cancels out. And that means that the effective phase of this two-photon transition, that basically when you try to define precisely or carefully what you mean by initializing your clock at a given time, is spatially dependent. Is spatially independent in the lab frame. And as we will see that in a moment, that will be crucial, because it means that what would correspond to the natural initialization time is something that corresponds, the constant phase hypersurfaces here would correspond to spatially, to the simultaneity hypersurfaces in the lab frame. So it really means then that you are initializing your clocks if they are at different spatial locations at the same time in the lab frame. And that will play a crucial role as we will see in a moment. So let's consider now the laboratory frame, the space-time diagram. We have these various sets, these two pairs of pi pulses, these acting as beam splitters, these diffraction gratings. And now, if you just initialize your clock at the very beginning, as I said, we will have this problem that the proper time along the two arms of the interferometer would be independent of the gravitational acceleration, little g, and we would not be sensitive to gravitational time dilation. However, if we actually don't initialize the clock initially, we just have it in the ground state, we apply the first two sets of laser pulses, diffraction gratings, that generate the superposition of spatially separated wave packets, separated by some different height difference here. And then after that, we apply this initialization pulse that I introduced on the previous slide. And then we just let it evolve and then perform this state selective measurement at the two exit ports. We extract for a given initialization time Ti, the phase shift for one of the internal states for the other, and then we look at the difference, the differential phase shift. And then we repeat the measurement, next shot, next experimental run. We do exactly the same, but changing the initialization time. And we again, perform state selective measurement here and here at the two exit ports to extract the phase shift for each one of the two internal states. We consider then the differential phase shift. And then with these two differential phase shifts that we obtain for different experimental runs, for different shots, we then take the difference between the two. And then you can easily convince yourself that the difference between these two is actually basically given by the energy difference, delta E, times the difference between the proper times accumulated along the two arms of the interferometer. So these two are simultaneously initialized to these two different times in the lab frame, and they have the same velocities along the two arms. So the difference in proper times is entirely given by the different gravitational time dilation, the gravitational redshift, which for an approximately uniform gravitational field is given by this. So just to calculate these, the key thing, as I said, is that the phase accumulated along the two arms is given by this, remember the previous formula, mn for each one of the internal states times the proper time along that path, and similarly here. And so then you're basically comparing for the two internal states, and the difference is delta m that corresponds to delta E times this proper time, and similarly for the other arm of the interferometer. And so this difference is then in proper time is what gives rise to to this quantity here. And just for this dashed line, corresponding to this dashed line, because in the first case, it would correspond to all this till the end of the interferometer, but then you have something similar for the second experimental run where you initialize at a different time. So then when you take the difference, these contributions after this initialization, they drop out, they cancel out, and you're just left with this contribution from the dashed lines. And so that's how you manage to get the sensitivity to the gravitational time dilation. Just to elaborate on that point, remember that I use this simple argument based on the freely falling frame to see that in general, your atom interferometer or quantum clock interferometer, if you were initializing before the interferometer sequence, was insensitive to gravitational time dilation. So let's understand in the freely falling frame how this result that I just presented, that gives you this sensitivity to the gravitational time dilation, the gravitational redshift in the uniform field, how can be that understood then in the freely falling frame? So again, in that case, everything are just straight lines which are independent of G. So where does the information on G come from? And this has to do with the relativity of simultaneity. So the crucial thing, if you remember, I already mentioned, is that you initialize your clock after you generated the the superposition of spatially separated atomic wave packets. And then the crucial thing is that it was done in a way that was simultaneous in the lab frame, okay, for the two arms of the interferometer, this initialization at different times. But that, due to the relativity of simultaneity, these two events, these two space-time events, which are simultaneous on the lab frame, they won't be simultaneous in general in another frame, the freely falling frame, which is moving with some non-vanishing relative velocity. And in fact, because this velocity is changing, as this is, freely falling in the gravitational field, then, the comparison between the lab frame and the freely falling frame, we will basically have this V that depends on G times the time that one is considering. And so this difference between times, this relativity of simultaneity that is well approximated for small velocities by this amount here, you see that it depends on this relative velocity between the freely falling frame and the lab frame, but that depends on the gravitational acceleration and the separation between the two arms. And so that's how you recover this result. And then, the difference in proper times along the two arms that you're sensitive to, it's just given by the fact that, they are simply not initialized simultaneously. And also this difference will change, as you initialize at later and later times, as illustrated in this diagram here. So then it's just the difference in proper times along for the two dashed lines here. It's trivial in this freely falling frame, but it's just that they correspond to different lengths because of this point here. And then, as you plug this result here, of course, you recover the result that one obtained in the lab frame before. So no matter which frame you consider, once you describe things appropriately and take everything into account, any quantity that corresponds to a measurable, observable, and measurable quantity, you should get the same result independently of the frame that you choose to describe to calculate that. And so we see that, with this scheme, one is able to address all these challenges that I had mentioned earlier. First of all, because we do state selective measurement and then measure the differential phase shift, we can measure this very precisely, much better than the small reduction of visibility for the reasons that I mentioned earlier. By initializing after you've generated the spatially separate superposition and comparing them different initialization times, you can be sensitive to the gravitational redshift, as I just explained. And also this additional difference between different initialization times also cancels additional effects that can be, for example, stable from shot to shot. So it gives you even further immunity to certain systematic effects and certain noise sources. And finally, you have basically no problems connected with the differential recoil. That has to do with the fact that, for the first pair of laser pulses, it's just acting on the ground state. So you don't have different internal states here. You do get an effect from the second pair of pulses. But the important thing is that, yes, that gives you, some slight difference in the trajectories for the two internal states, but that's acting exactly in the same way for the different initialization times. So that's an example of things that when you consider the doubly differential measurement scheme, when you subtract the results, the differential phase shifts for different initialization times, those things drop out, those effects drop out. So that's not really a problem. And so that's how you can address all these challenges. And just, to mention how feasible this is, you can plug the numbers and see that with these atomic fountains, 10-meter atomic fountains using strontium or ytterbium atoms that have the right structure are used for optical atomic clocks, and they would fit these kind of experiments I was mentioning. And the numbers, you can see that, with parameters that are, certainly feasible, that have been demonstrated, you can get a signal, a contribution from the gravitational redshift that corresponds to differences in the differential phase shift of the order of a few milliradians. So that's something that in the best case, where you can have tens of thousands of atoms, you could measure ideally in a single shot, but in reality, where you have maybe a little bit smaller number of atoms that you finally detect, and you might have some other additional noise, technical noise sources, you might need to do that in tens or hundreds of shots, but it's something that you can certainly do in principle. And since I see that, oh, we started a little bit later, but so now basically the point is that I have this alternative implementation discussing also a bit more the details of how to do that, for example, with this atomic fountain in Hanover. But I'm not sure whether I should jump to the conclusions and then I leave a bit more time for questions, and in particular,
But it's okay, it's up to you. You can, if you want, you can briefly mention it. Go ahead.
Okay, so then this variant that I'm mentioning here, there are ways to implement what I just said before, also with the experiments like the new atomic fountain that will be available in Stanford and some other facilities. But you know, one still needs, there are some in practice, some things that make the implementation not completely straightforward, and they have to do with this point here, which is the following. So the challenge is that, at least for the second pair of pulses, as I mentioned a moment ago, you apply them when you have already generated the internal state superposition. And so what that means is that you need those laser pulses that act as diffraction gratings to diffract efficiently both internal states, you know, at the same time. And that's something that, you know, in general, you choose the frequency for your laser pulses suited to diffract efficiently your atoms in a particular energy state. So that's something that is done, and you can choose it properly. But having a laser pulse, a single laser pulse, or the same beams with a given laser frequency that can efficiently diffract these two different internal states in this context of this, where you can get the large signal. So for these energy differences that will correspond to an electron volt, these states that are used in optical atomic clocks, that is not so easy. So that you have basically two ways of doing that. One is using Bragg diffraction, which is, I could elaborate that later on, but the key thing is that in order to make sure that it diffracts efficiently with similar efficiency, with the same efficiency, both basically that acts in the same way on the two internal states, because in fact they feel exactly the same optical potential. That's something that happens at the so-called magic wavelength. It's something that is exploited by atomic clocks, also for other reasons. By optical atomic clocks. But the main point is that that requires, because this wavelength is far detuned from any transition, you need a lot of laser power to implement these diffraction gratings. So it's something that in principle you can do, but that's a lot of laser power. So that goes beyond the simple implementations that you could use right away. There are some other alternatives based on single photon transitions, which are also another possibility. And it's certainly something that in a few years should be possible to implement. But in the near future, you know, it's something that is still being developed. You need fermionic isotopes, they require higher complexity. So it's something that is far from maturity, at least in the, you know, it will take 5-10 years to develop that to the level where you could do these experiments. So based on that, you know, I looked at some alternative scheme that overcome, so that can be implemented with much simpler atom optics, these diffraction gratings, and with very mild requirements on laser power. And they could be implemented in principle right away with this VLBAI facility, this 10-meter atomic fountain that is becoming operational in Hanover. And so just again, maybe this is also useful, just again, this diagram of the scheme that I presented a moment ago. Notice that here I'm using slightly different notation for my picture. So magenta and orange don't correspond to the two different arms of the interferometer. Now they correspond to the two different internal states so that we can see better what's going on there. And so what you see that when we apply at some initialization time, we have now the superposition of the two internal states from this point on, so magenta and orange. You would measure then, you know, this differential phase shift with state selective measurement, and then you would repeat that for a different initialization time, measure this other differential phase shift, and then compare the two, and you get this result that I mentioned before. Now, the problem is that it has these nice features I mentioned, you know, of cancellation for every single shot of things like the vibration noise and so on, but we have this challenging that I mentioned a moment ago. So then the idea is that can we find some alternative that could overcome that? And motivated by that, one could say, well, okay, so let's give up for the moment this nice feature of having the two internal states simultaneously, measuring these phase shifts for the two internal states in a single shot simultaneously. That has these nice features of canceling out vibration noise and things like that. So let's drop out that for a moment. Then of course you have a natural way of doing that. Instead of a pi-half pulse that generates an equal superposition, equal amplitude superposition of the two internal states, you can have a pulse, initialization pulse, which is twice as long. Then it's really a pi pulse, it's an inversion pulse. So basically you start in the ground state and then you basically excite all the atoms to the excited state. And then you just follow, as before, and measure the phase shift now for the excited state, d phi 2, or d phi a here. And then what you would do is that you could now do similar setup, same thing, but now applying no initialization pulse. So everything would be in the ground state. And so in this way, you would be able to basically do the same as you did before if you now change the internal state, but measuring the phases for the two internal states in different shots. That per se is not good because it was good to do it simultaneously to cancel out vibration noise or things like that were not stable from shot to shot. But what we see is that if we do it in this way, then instead of just applying this inversion pulse at different times, what we can do, in fact, is that we can actually just apply for this interferometer a second inversion pulse at some later time, TF, in a single shot. This is something that you can do now because you are just in a given internal state. You could not do that in the previous scheme. But if you are willing to consider splitting the measurement for the two internal states in two different shots, then you can certainly apply it like that. And this has the nice feature that then, in a sense, in a single measurement here, because you have initialization time and final time, you can be sensitive to this gravitational time dilation between the two arms of the interferometer. You still need to compare, with the second shot where you have it in the ground state to really get the measurement. But the really nice feature is that because of this second inversion pulse, now when you apply the second pair of diffraction ratings, they are again applied to the ground state. So then in this shot, for all pulses in this shot, and also for all diffraction pulses in this shot, they always act on the ground state, and certainly not on a superposition of the two internal states. And so then it's straightforward to implement good diffraction pulses that are efficient, acting on the ground state, for example. And this is something that, for the kind of atoms I was mentioning, like ytterbium, for example, has already been demonstrated that you can do that very efficiently and even give good momentum transfer and so on. And so in that sense, that's good, because then we do no longer have that problem I was mentioning about the diffraction pulses being efficient. And now they always act on the ground state. And so that can be done very efficiently. By the way, here I'm mentioning also the fact that so far I mentioned the results if you are in standard general relativity, but you can also consider possible violations of the gravitational redshift, the universality of gravitational redshift. And so you can have parameterizations of deviations from general relativity, for example, with dilaton models. And this is the result that you would get then in cases like that. So this is a parameter that then parameterizes these violations of the equivalence principle of the universality of gravitational redshift, and the deviations from general relativity would be this alpha that would be 0 in general relativity. So you can extract that directly from this kind of measurements. And this is how you would implement it in ytterbium if one is interested in practice. The two clock states, then you would have these pulses, these two counter-propagating photons illustrated here with the same frequency corresponding to half the transition frequency between the two clock states. This would be for the inversion pulses or the initialization pulses before. And then you would use these two beams, counter-propagating beams with slightly different frequencies that are used to implement the standard Bragg transition for the ground state. Okay, and this is something that has already been demonstrated in other experiments that can be done very efficiently for ytterbium using this transition here. This is a diagram of this atomic fountain in Hanover that we are planning to use for this experiment, my colleagues in Hanover. And so this would be the experimental, the key aspects of the experimental implementation. But there is one point that one still needs to address, because remember, we managed to do this, but giving up the fact that one was measuring the phase shift for the two internal states in a single shot. So now we have small changes of the gravitational field in time from shot to shot, for example, due to the tidal forces that are changing, the tides and various, we're measuring really tiny effects. So it's important to keep those things in mind. Or more importantly, the vibrations of the mirror. These beams are retroreflected at the bottom with the mirror here. And even though one has good, vibration attenuation systems and so on, vibration isolation, to get to the level that we want, it's not something that you can achieve in a reasonable way. So you need some way of suppressing this vibration noise, at least at some level, even if it's a small level of vibrations. And that was done very naturally with the common mode rejection when you perform the measurement in a single shot for the two internal states. It's not possible here, but what you can do is the following. So these would be the two different shots that I mentioned before, and these would be the contributions that would be problematic. One that involves small changes of the gravitational field, delta G here. Here I just for simplicity assume that it changes, but it's constant for the different shots. It changes from shot to shot, but it's constant. But even if it's time dependent during the shot, you get a similar expression just with a double integral. No substantial change. And more crucially, or even more importantly, these contributions from the vibrations of the mirror. Right, so that's the problem. But actually, the way to address that is that you can simultaneously perform, and that's something that this atomic fountain is equipped to do. It was already designed to do that for other reasons. It can simultaneously operate an interferometer with ytterbium atoms and an interferometer with rubidium atoms. And so what you can do is that you can do this simultaneous, differential atom interferometry measurement, which is something that is done for other reasons in experiments. And you can simultaneously, apply laser pulses that diffract your atoms in the ytterbium and for rubidium. You use different frequencies, simultaneously beams with different frequencies acting on these two different atoms. That's something that you can do. And basically the idea is that you use then a rubidium interferometer, which would have exactly the same form as for the ground state of your ytterbium atoms, with laser pulses applied, with the same time separations, but some different frequencies that would, efficiently diffract the rubidium atoms, but basically do nothing to the ytterbium atoms. And what you do is that then you can basically measure these, you can see what is the contribution from the rubidium atoms, and it takes basically the same form as here. But, with the effective momentum associated with the frequency of the laser beams that you use to diffract the rubidium atoms, which in general will be different from ytterbium. So what you can do is consider the difference between the phase shift measured for a given shot for the two atoms with this suitable rescaling due to the difference in frequencies of the laser beams that you use to diffract rubidium atoms and ytterbium atoms. And then you can see that by you doing this in a given shot, you do this, for example, with interferometer of the kind A for ytterbium and the interferometer for rubidium, and then also interferometer of the kind B for ytterbium and a similar thing for rubidium atoms. And then you can just see that then, these terms here would cancel out for every shot. These two contributions, these problematic contributions here would cancel out. And then when you compare different shots, you recover the result that you were interested in. And the contribution from the rubidium atoms basically also drops out. Its only role was to act as an inertial reference, basically to get rid of these small changes in the gravitational potential and also the effects of vibrations of the mirror. And so in this way, you can measure the gravitational then time dilation, or also, for example, check for possible violations of the universality of gravitational redshift by deviations from GR, which is something that is, a standard thing done when comparing independent clocks. The nice thing is that you would do it now in the quantum regime, with clocks single clocks in a superposition, which is spatially separated and fitting different gravitational time dilations. And you can find here, the details of this experimental implementation, which should be then feasible with this atomic fountain, this facility in Hanover, Now, in this case, it involves a much simpler atom optics with mild requirements or very mild requirements on laser power. And the key thing, of course, is that in this scheme, you need some way of suppressing this vibration noise. And the idea is that you do that by using simultaneously an interferometer with rubidium atoms as an inertial reference. But this ability of operating simultaneously ytterbium and rubidium was something that was already early on, for other reasons, in the design of this facility in Hanover. And with that, I just finished with the conclusion. So I showed you that there are actually promising ways of measuring these relativistic effects in these macroscopically localized quantum superpositions. And I explained how there are actually important challenges to do quantum clock interferometer experiments that are sensitive to gravitational redshift, but how this can be, successfully overcome with this doubly differential scheme or variants of that. And then its implementation should be feasible in facilities that are becoming operational right now at the moment. And these are some other couple of publications, also related work to what I presented here. And with that, I thank you very much for your attention. And I'm glad to answer other questions that you may have.
Thanks. Thank you very much, Albert. It was very nice talk, very interesting. So please, from the audience, if you have any questions, this is the time to ask.
So let's thank Albert. Yeah. So very interesting. So maybe can I ask one question? So initially in your first scheme, not your second scheme, that you had this initially uninitialized like random internal states, right?
Not random. It's really the ground state.
Ground state. Okay, I see. In both the schemes, you had ground state initially.
Yes.
And
in both cases, you start with the ground state, which is actually might seem, but actually that's easy because you really cool these atoms and so on. So it's actually very natural to start with the ground state. So
okay, and then at a certain time, you come with the laser and excite, right?
And initialize, yes, generate this superposition or invert the state in the second case.
So the precision of your measurement, is it in any way affected by the time precision of the laser pulses, like their rise time or fall time?
No, this is interesting. So no, it's you would think that, or you might be worried that you need to control these initialization times very precisely, but that's actually not the case, because the crucial thing is that the initialization is happening, with that precision for both internal states. But then if you actually change this initial time slightly, that's basically what that would mean is that this TI here would change by a small amount. But the quantity that is small, so this difference, let's say, is of the order of a second, for example, is really small because of this pre-factor here. And so a small change here for sure would give a tiny, because it would be the uncertainty in this initialization time times this small factor here. So you see, you have this thing which is of order of a second, and then it's suppressed by this small thing that makes the measurement, not impossible, but something that is non-trivial to perform. So then this small change here is not a problem. Crucial thing there is that, as I said, that this is happening for the two internal states, kind of at the, well, even the other state is unchanged. So it's really not important. What is really crucial is that it is done at that level simultaneously on both arms of the interferometer. That is certainly a crucial point. So it's crucial that basically this initialization here is happening simultaneously on both arms at this level. It should be, if you remember then the argument from the point of view of this frame. So you need to have this difference in time need to be much smaller, if there was any, than the difference in proper time between the two arms of the interferometer, for sure. That's certainly crucial. So that's why the role of this initialization pulse is really important. And so it's important that it acts simultaneously on both with very good precision. And that's really based on the fact that you need to make sure that the frequencies of these two photons are the same with a very high, precision. And because that then makes sure that, the spatial dependence here cancels out. And the way one would do that is that, well, also taking advantage of this mirror that you have anyway there for other reasons, also for the standard diffraction pulses and so on, is that you send your very monochromatic laser beam and you reflect it off the mirror, and then that guarantees that the frequencies are the same. Of course, you can look, for example, at small vibrations of the mirror, but even though they give effects on the phase, possibly, that are relevant for the diffraction pulses, and I discussed at the end the need then to use the inertial reference, the rubidium atoms as the inertial reference, but for the frequency, the change of frequency with these small vibrations of the vibrationally isolated mirror, that's much smaller. So it is a level where this is not causing a problem here. But that's one of the crucial points. You need to make sure that the initialization is simultaneous on both. And as I said, when you really try to be careful about what is meant, because of course the duration of this pulse in these implementations will be of probably 1 millisecond or slightly longer than that. It's longer than other laser pulses, but here it's important that it's this so-called Doppler freeze. So it's really not sensitive to some effect which is called velocity selectivity of the usual laser pulses used for diffraction. So that's one thing, but I mentioned that they are long. I was trying to, yes, right. So what is meant by really the initialization time? So that also has to do with when you use clocks, and at least in some of the configuration, the usual atomic clocks, where you have a single clock, and you just generate this internal superposition to measure basically, what we had here, right? And you, with a single clock, you just initialize, and then you try to basically read out in some of the schemes. You also need to make sure that what you mean there by when you try to measure these times, the level of a fraction of 1 in 10 to 18, 1 part in 10 to 18, what do you mean? It's certainly a time which is determined much, much, much more precisely than the duration of these pulses, which are usually relatively long pulses. So the key thing is not so much the envelope and the center of the envelope. That duration makes sure that you have, for example, equal amplitude here. But what determines really what you mean by at what time you initialize is really the phase. So you have this envelope, but then you have this envelope that is, modulating the envelope of something which has a much higher frequency that would correspond to delta E over H bar. And so what really determines what you mean by the initialization time is exactly this phase that is modulated by this envelope then that gives you a much longer pulse. So what is really meant, but at what time you initialize is really exactly given by this higher frequency wave that is modulated then by this envelope. And that's something that, for example, when you try to make sense exactly what is meant of these atomic clocks and those measurements and what is meant by initializing and reading out, it's really this phase that is then modulated by this envelope that is really what determines, very precisely then what these frequency differences or these time measurements. And here it would be similar. In fact, here, the only related to your question again, the crucial thing is not so much the absolute time, but just making sure that this is happening simultaneously on both arms at the same time. And that is really connected that in the lab frame, as I said, the Ks of these two counter-propagating vectors are exactly the same. And so they cancel out. And that makes sure that in this frame, basically the equal phases correspond to points which are spatially separated. And so these simultaneity hypersurfaces in the lab frame would correspond to constant phase. And as I said, when you look in details, initializing at the same time means that the phase is the same on both arms at the same time in the lab frame.
Thank you. Thank you very much.
You're welcome.
So maybe others have, Igor and Miles have some questions, I think.
Go ahead, Igor.
Miles seems to be the first one.
Okay.
Well, I think, or maybe, I'm sorry. I mean, on my screen, Miles appears as the first one, it seems.
I already asked a question before, so I'll let Igor go.
So then Igor.
It's very polite, although I do think Miles was first to raise, but I'll ask, it's actually a quick question. So first, thanks a lot for the talk. I mean, it's very nice. Also really nice to see, you know, broader interest in clock interferometry and new ideas and closer to experiments. So this is really great. And what my question is also an experimental one a little bit in the following sense. So you explained nicely how one can deal with these internal states practically, specific implementations, and you know, a lot of the subtleties that need to be overcome and how to do that. And one thing, and maybe you mentioned it, I missed it, but one thing, for example, even on this slide, one issue is of course also with the fact that the effect always depends on the overall accumulated proper time difference.
Mm-hmm.
You know, that's always the case. But for example, depending on what type of geometry there is for the implementation, for example, like a Kasevich-2 type interferometer, it's made exactly in such a way, even though you have different heights and so forth, that there's a two lowest order cancellation effect in the sense that the proper time difference is actually pretty small. So you always have some, but it's not necessarily always, you know, the high difference as it would be if you keep it.
You're absolutely right. So this, well, maybe this was not the end of your question, but so please go ahead. I'm just looking for the next slide.
It's nearly the end. It's basically about that, just somehow to optimize also the high difference. So if one were to hold it, that's of course one way, but this, you know, we know it can be done, but very small. But here, yeah, so yes, exactly. So there's a Ramsey-Bordet that could be done, right, or other geometries that would be best, so basically.
Let me explain. So this example I used here was to actually show an example where you do have a non-vanishing proper time, although it's not sensitive to little g. But you could, of course, have this Mach-Zehnder interferometer, which is actually the one that is also very often used. Let me see, I have it here, more or less. So this one here, except that usually you use the same time between the first two passes and the last two passes, so that then this was just to illustrate that in general you can have some relative displacement between the interfering wave packets. And in the standard Mach-Zehnder, typically one has the same times here, so it would be the same, but where this, you know, then would coincide, there would be no relative displacement. And then, as you said, it's completely symmetric. So there are 2 points here. One is that in this case, there is no, in principle, proper time difference between the two arms, ideally. But that doesn't change. So in this case, there is a proper time difference, but it's purely, you could say, corresponds to spatial relativistic time dilation effects. Whereas in this case, in principle, not even that would be present. I mean, when the times are the same. But in both cases, that's a crucial thing. And this is connected indeed to the challenge, the main challenge that I was mentioned. In both cases, no matter which, I showed just examples, but you could consider a completely generic sequence of diffraction pulses here. And you could do the general calculation, or you could just intuitively understand that in the freely falling frame. And you would see that in all cases, you have these straight lines. You might or might not have proper time differences between the two arms of the interferometer, but they would always be spatial relativistic. They would not be sensitive to little g. That's of course based on, if we try to be then very careful, first of all on the result that would be for a uniform gravitational field. In reality, you will have small deviations from uniform gravitational field, but you can see that for our interest, you know, for our purposes here, would give you much smaller effects. That would not, the signal we are trying to measure is already small for the dominant effect of little g. So the contribution from the gravity gradients would be there, but they would give you even smaller contributions. So they certainly actually have a slide at the end, but I don't want maybe to get too distracted, but once you consider gravity gradients, you do get differences in proper time. And maybe I can even mention that they have, in a sense, been measured, but not in the context of quantum clock interferometry. So if there is interest on that, I can elaborate in a moment. I have a backup slide at the end. But before getting to that point, yeah, so then there is also an additional point which has to do that here, I'm not describing in details these laser pulses acting as diffraction gratings, but of course, their timing and so on does depend on little g when you change from frames. So these are details of small contributions when you change between different frames that do depend and would give rise to some contribution to the difference in proper time that would be sensitive to little g, but they would be corrections of higher order corrections. They would be suppressed compared to the signal of interest by an additional factor of 10 to minus 10 or so. So if you really get into the technicalities, this statement I wrote here is only true up to certain corrections at higher orders that are certainly suppressed. So in that respect. But otherwise, I would entirely agree with you. It's in a sense that the point of this, and the crucial point in this slide, namely the fact that except for these tiny contributions that would be too small for what we are interested in doing here, the proper times would be either the same on both arms, for example, for the Mach-Zehnder case, or even in cases like this one where they are different, they would not be sensitive to little g, except for these much smaller corrections. So it's really, I fully agree with that, but that in a sense is not something that is being exploited here. This is one of the challenges that one tries to address. And in fact, this scheme here, notice by the way that this is not exactly the Ramsey-Bordet here, it's the inverted one. So this was just to illustrate, it would be the one where instead of, like this, the second arm would go up like that. So it would be in that sense similar to the Mach-Zehnder. In the freely falling frame, the proper times along the two arms would be the same. The crucial ingredient then is not so much the choice of Ramsey-Bordet versus Mach-Zehnder, but it's really the fact that you initialize your clock after you generate the spatial superposition. In that respect, it's sure good to use this inverted Ramsey-Bordet rather than Mach-Zehnder, because you have then this nice sort of time between passes where it's, at constant, the relative separation between the two arms remains constant. So in that case, in that sense, it's convenient, but otherwise, the proper time in this example here, as I said, if you were just initializing at the very beginning, it would be the same on both. So it would be the same as for Mach-Zehnder. Because of the scheme you use here, in fact, here it doesn't matter. You could use either this or the one I mentioned in the previous slide, and it would work the same. In fact, some of these things can be exploited in an actual experimental realization, because the nice thing is that you can change many things here and make sure that it should give you the same result, and make sure that indeed you get the same result. For example, you can compare measurements like this, but where this difference between the two initialization times is the same, but now you do exactly the same, but with pairs where the initialization times, as I said, the difference is the same, but maybe you started a little bit earlier or a little bit later, so that the result should in principle be the same, but in reality in experiments, you have systematic effects and things like that. So changing all these things, like going from this Ramsey-Bordet or the other one, are useful ways of checking your double checking for consistency of your measurements. But the key thing is indeed, these proper times can be in this case, for example, the same on both, or generically, even if they are different, they are independent of G, except for these very small contributions. And that's what's overcome, or that's what's addressed with this initialization after you generated the spatial superposition.
Thanks.
You're welcome. And then, as I said, if anyone is interested, actually, once you go away from, or you take into account tidal effects, deviation from uniform fields, actually, then you do get non-vanishing proper time differences. So I'm not sure if there is interest, I can show you a backup slide where this is mentioned.
There's certainly interest on my side, but maybe, for the sake of time, I don't know. Maybe we can get back to it later when Miles gives his
I'm sorry,
question.
I forgot about, because Miles lowered his hand. So you're right. So I'm sorry about that. So yes, I think we should then go to Miles' question, because your virtual hand was lowered, and then I forgot about your question. I'm sorry about that.
But I just, if any, I just have one more speculative question, and because you're limited when working with single atoms, you're limited with the delta E due to the internal states of that one atom. Has there been any thought in the future about working with a cloud of collectively excited atoms so that you have a scaling of n
Oh, well, so
and delta m or something like that.
So,
so it's like cloud interferometry or.
Yes, so I guess what I can say are two things. One is that the simple one is that in practice, of course, you do these experiments not with one single atom at a time, but you actually use an atomic cloud with 10 to 5, 10 to 6 atoms in the best case that I was mentioning.
Yeah, because you mentioned that and I was a bit confused because it
Right.
seems like it's a single atom interferometry in some sense.
Right, so what I tried to do first was to really emphasize the difference between comparing it, even when you compare independent clocks in reality nowadays, except for the ion clocks, trapped ion clocks, which really involve a single ion. The usual optical atomic clocks, which are based on trapping neutral atoms in optical lattices, they all involve typically at least thousands of atoms. So really in all these cases, you have actually not just a single atom, but many of them. However, I was trying to emphasize that in that case, what you have is not just comparing two independent atoms, but really two independent collections of atoms in that case. Or in this case, what you have is a collection of atoms, but each atom then is, experiencing what I just showed here, is split in a superposition, which is basically then has this, for some time, this difference in height between the two arms of the interferometer, and then it's recombined. And the whole interference in these setups that have been realized so far, I mean, with atom interferometry, and that we plan to do here, basically the interference is happening at the level of single atoms. And then you just have a collection, an ensemble of many different atoms, but each one of them is experiencing this. An interesting idea beyond that, not even for these experiments, but even just for simpler atom interferometry, and it's something that there's a lot of interest in doing, is that eventually not using initial states where the atoms basically can be regarded as independent or as if they were independent, even when you have BECs in practice in the end boils down to something like that. It's to use some squeeze state, some entangled state. Because then indeed you could actually, so when I estimated, for example, this short noise sensitivity, that number I mentioned before of 3 milliradian, or how to read 3 milliradian with 10 to 6 atoms, that's based on the standard quantum limit, 1 over square root of it. So you get milliradian with 10 to 6, square root of that, 10 to 3, and that's how you get the milliradian in a single shot. But of course, if one day one can control these entangled states, and you can go beyond the standard quantum limit and use the Heisenberg scaling, then that would be much better, because with the same number of atoms, you could actually gain, get a big gain in sensitivity. This is something that where there has been already very interesting progress for internal states. So for just the clock, but not interferometry of center of mass, degrees of freedom. But it's something where there is a lot of interest, and there's a lot of interest to explore this idea. It's not straightforward. As I said, there have already been some interesting demonstrations just for superpositions of internal states, but like the usual atomic clocks where you have the atoms, kind of trapped or just located there, not the scheme, the quantum clock interferometry scheme that I presented here. But for center of mass, degrees of freedom, that's something that there's a lot of interest. It's still, it will take some time. But then you could achieve in this improvement. So you could apply these quantum metrology techniques to enhance the sensitivity.
Thank you very much. It's
and
very interesting.
You're welcome. And of course, you could try to exploit that also in not just with a standard atom interferometer, but in a measurement scheme like this here.
Right.
Good, very good. So I think we have had enough questions, and I think maybe we should thank, if there's no other question, then maybe we should thank Albert again for this very exciting discussion and very elaborate discussion. So thanks.
Thank you very much for your very interesting